Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 181, I chat with SpectraCal CTO Derek Smith about the importance of calibrating your computer monitor to match your TV. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CacheFly.com.
This is Home Theater Geeks with Scott Wilkinson, recorded November 4th, 2013. Episode 181, Getting the Most from Your Monitor. This episode of Home Theater Geeks is brought to you by iFixit. You can fix it, and iFixit makes it easy with step-by-step repair guides, high-quality replacement parts, and all the tools you'll need. For $10 off your purchase of $50 or more, go to ifixit.com/twit and enter the code HTG at checkout. Hey there, Scott Wilkinson here, the Home Theater Geek and Director of Content at avsforum.com. This week's guest geek is Derek Smith, the CTO and founder, one of the founders of SpectraCal, makers of CalMan calibration software, very widely respected, very widely used in the calibration business, to talk about what else? Calibration. Hey, Derek, welcome back to the show.
Thanks, Scott. We enjoy being on your show. It's been a while. We've got a lot of updates that's been happening in the industry and our products, so we've got a lot to talk about today.
Indeed, we do. Before we get started, though, I want to make sure that everybody knows that those who are tuned in to the live stream at live.twit.tv or logged into the chat room from there or at irc.twit.tv can post questions, and I'll pass along as many as I can during the show. Okay, now CalMan, the software that SpectraCal has been developing for several years, is now up to version 5.2. Am I right about that?
5.2, yes. We've had a 5.2 release candidate out for a couple of weeks now. I sat down with the engineering team this morning, and we're going to have 5.2 final release out this Wednesday.
Fantastic. And one of the really cool and interesting new features in 5.2 is the inclusion of, I guess, ICC profiles. Have I got that right?
In kind of a nutshell, yes. The ability to calibrate your PC monitors or Mac monitors, whether it's the laptop itself or monitors that are connected directly to them, we're able to calibrate them with the CalMan core now.
Excellent. So this is actually, believe it or not, Leo Laporte, the chief twit and all of our mentor here, the inspiration for all of twit, has a radio show on the weekends, and someone called in with exactly this question. They're a photographer or a videographer, I forget which, and they wanted to know, why is it that when they work on their photos and videos on their computer monitor and then take it over to their TV, it looks completely different. And then when they go to print it out, it looks completely different still. And so I thought it would be very useful, and how timely that Leo took a call about it this very weekend, about how do you consistentize, if I may coin a term there, your video monitor, your computer monitor, where you might be working on photos and videos, with your TV. I deal with this myself. I'm an amateur photographer, and I take a bunch of pictures, and I want to show my family, some of the work that I've done, and I tweak it all up, and then I take it over to my mom's house, for example, and show them a slideshow, and it doesn't look the same. So I've always been kind of confused, and how do I deal with this myself? And here you are coming along giving us a solution. Why don't you start by giving us your hit on the problem and why CalMan needed to address it?
First, I'll talk about kind of the history of ICC, or what ICC even is. A lot of people may hear this term but not really understand what they're getting or what it was for. It was originally founded back in 1993, and it is the International Color Consortium, and it was founded by, I believe it was 8 or 9 industry companies that said, we're having this problem in the field. People are using scanners, they're using printers, they're using computers for either industrial or desktop publishing, and in no one place does the image look the same. They all look different. So my colors that I scanned in, that I had an artist rendering for a greeting cards company, I scanned them in, I brought them up on my monitor. It looks different. So I do work on my monitor, and then I go to print it out, and it looks different again. And they found that they were getting different colors or looks along the way. So this consortium came together and said, okay, as an industry, we actually need to fix this problem. Tom Lianza, one of our good friends of Spectre Cal, we know very well, was one of the co-chairs and still is today of ICC. He founded a company called Sequel Imaging. And if you remember back probably 10 to 15 years ago, he came out with these affordable colorimeter, something you could put on your monitor to measure it, something you could put on the printer output to measure it, something that could analyze the input from a scanner or a camera. And that was kind of the beginnings of ICC, was to basically say, we want a consistent color space no matter whether it's an input device or an output device. And so that was the goal, so that if you did your desktop publishing on your computer, then if you took it to other places, it looked the same. You basically got the same intent. This worked very, very well because we had CRTs until about 10 to 15 years ago, and we started coming out with other display technologies. CRTs perform in a very consistent linear fashion. We know what the gamma curves look like. We know what the gamuts look like. We know what the color rendering engines and how they worked in CRTs. And so ICC works very, very well in a linear space. If we fast forward to today, we have LCDs and plasmas and OLEDs, and now quantum dots are coming out and all these backlight technologies, and they can perform digitally, which means the manufacturers can creatively mimic a CRT, or they can kind of come up with their own way of reproducing color and grayscales. So the need for ICC is even more imperative today. Most people have noticed if they've went out and purchased a Mac or a PC laptop or MacBook in the last probably 3 to 4 years, they've been advertising that the output of these displays are much wider viewing angle. They're very bright. You know, they come up with all these things. They're very thin. They're very power efficient. You can run for up to 8 hours, 12 hours on some of these devices now. How they did that is they switched over to LEDs as the backlight. But LEDs typically don't produce native white. They either produce red, blue, and green, or they produce a blue that's been doped with a yellow. And if most people notice now, sorry, go ahead, Scott.
I was just going to say, that's what I thought when most TVs anyway, LCD TVs that use LEDs for backlight, which is virtually all of them now, they have a white LED behind or to the sides, to the edges of the LCD screen. But the white is actually produced by blue LEDs that have yellow phosphors on them that and blue and yellow actually can combine to make white. But are you saying that it's not exactly a perfect white?
Well, what you'll find is it is a white, but it is a very blue white. And so if you look at our color temperature curve on our CIE chart, you know, whites can be anywhere from a daylight white to a reddish white to a bluish white. And by using a blue LED with yellow phosphors, they ended up with a white that is very, very blue. It's bright, but it's very blue.
This may explain partly why they did it that way, because TVs in the showroom, you know, like a Best Buy or something like that, you know, you got this wall of TVs, and they always need to be as bright as possible and as blue as possible, which tends to attract the eye more. So maybe that was an advantage to them, to the TV makers, in terms of the ability to attract buyers on a showroom floor, not necessarily for accurate white or color, though.
No, that is correct. And since they were manufacturing TVs, the panels for PCs kind of adopted that technology. So now if you buy a laptop, a MacBook, or you buy a monitor for your PC, they're all using LED backlights typically now, and they're all very blue from the factory. So this problem of being able to create an ICC profile or calibration for your PC monitors is even more imperative today, because they're not CRTs, they're not a known space. The manufacturers are all over the place, depending on which manufacturer it is, on the colors that they can actually produce. And so we had a number of customers, probably in the last 4 or 5 years, come to us and say, hey, you've got this calibration software for televisions and displays and projectors. Can't you just do it for computers? And the answer was, yes, we're working on the technology, but it's not as easy as just adding some existing technology to our base. We had a fair amount of work to do to wire this in. But we wanted to be able to create a comprehensive solution so that if you're a CalMan user and you have the add-ons for CalMan, or CalMan RGB as the product it is, you can calibrate essentially everything in your house. So you can calibrate your computers, you can calibrate your TVs, your projectors, you can calibrate everything to whichever standards that you need.
Now, pardon me for interrupting, but why would you need new technology to calibrate a computer monitor? Wouldn't it be the same as calibrating a TV? I mean, don't you want D65 white? I mean, these are terms that are just the names for the standards that we use. D65 white, Rec 709 color gamut, so on and so forth. What's different about computer monitors that required new technologies and so on?
There is a fundamental difference on how computer monitors work and the color space that we work in. For one, the video range. You know, we talk about video range in the digital world. We've got 16 to 235 of 255 steps of black or white that we can work in. On computers, they didn't need the headroom and toe room, so they expanded that out to 0 to 255. So they have more of a dynamic range than what our video monitors are capable of.
Okay, that's a good point. Let me just make sure everybody understands. The brightness of any video signal is represented in some number of bits in the digital world, and now we are, of course, in the digital world. And up till now, it's always been 8 bits, which gives you 256 steps. In the land of video, black starts at a value of 16, and white ends at a value of 235. So that gives what Derek called headroom and toe room to be able to extend beyond black and white if you really need to. Computer monitors don't do that. They use the entire dynamic range to begin with, 0 to 255.
Yes, so that's one fundamental difference. The next fundamental difference is the gamut, or the number of colors, or the color space we're actually working in, is different for computer-generated graphics versus video. We talk about video space being, D65, Rec 709, D65 being the white point. What colors do we want our whites? Do we want them red, or we want them blue, or we want a daylight white, which is what D65 is.
Right.
The 709 is the color gamut. How much color do we have? What is the full saturated colors of our red, greens, and blues? 709 for video is well defined for our high definition standard. But for computers, they've also got sRGB, which is a derivative of 709, but they also have Adobe RGB, which is a much, much bigger color space to work in. So if you go out and you take pictures with your camera, your digital camera, and you bring them into your PC, and you see very vibrant blues and reds and greens and all the colors in between, and then you take that same image and you put them on your television, if your television isn't set up for reproducing Adobe RGB, those colors are going to look washed out.
That makes sense. Because the color gamut, the range of colors, space of colors that the camera can capture and that the PC monitor can reproduce cannot be reproduced on a TV, which is why they'll look kind of washed out, and maybe the reds will look a little orangey, maybe, or something like that.
That is correct. And so we started addressing these problems within CalMan RGB, the piece that's specifically designed for calibrating PCs and Macs. And within that, we took ICC, but we actually are calling it ICC Plus now within our product. And we encompass the ability to create multiple color spaces to work in. So if your primary job is a photographer and your primary output is paper, printed photos, then you can set up your computer to say, well, I want Adobe RGB because that's the space I'm working, and I'm using Adobe tools for editing my photos. But I'm also going to set my printer up to reproduce Adobe RGB. So everything I see on my monitor reproduces exactly what I see that's coming out of my printer that I hand to my customers. If you are using a display for playback, you bring your customers in and say, hey, here's my big plasma or LCD or even a projector, and say, this is what your wedding photos look like. You need to make sure that either the display was calibrated to Adobe RGB, some are capable of it, most don't have that much wide gamut, or On your PC, you shrink its gamut down and you work in the 709 space and you do all your correction in 709 on your PC. So when you put it on displays that are 709, they match.
Mm. Well, you're right about the fact that most consumer video displays, TVs, projectors, and so on, can't reproduce Adobe RGB. And those that can, maybe it does in red or green or blue, but not necessarily all of them. The expanded color gamut, which many manufacturers tout and say, look, we can do more than Rec 709. But how much more? Exactly what are the boundaries of this new space that they can do? It's different from one to another. There's no consistency.
Yes, that is correct. And even in the video space, we also have what's called DCI P3, basically digital cinema. Their color space P3 is a very large color gamut, much bigger than 709, but it is different than Adobe RGB in that the greens are in a completely different space. They're about equally as big, but the greens in P3 are shifted towards the blues, and in Adobe RGB, they're shifted towards the reds. And so those aren't compatible with each other either. And so within CalMan RGB on your computer, if your display is capable of it, you can say, I want a DCI P3 color space. I would like to have a Rec 709 color space. I'd like to have an Adobe RGB color space, or any other color space that you could possibly need for coming up with that. So you can use your computer for editing videos, for editing photos, and then also set them up for playback on any other device.
Now, I must tell you, I'm not that familiar with computer monitors, so I wonder, do they typically offer the same sorts of color management systems and calibration tools or controls that TVs and projectors offer that allow you to move the color points and the white point around to match these different spaces like sRGB or P3 or Adobe RGB or 709, all these things we've been talking about. Is that easy to do, or do you have to do that from the outside with some sort of external processor?
Typically for computer monitors, you have to do that from the outside. You can kind of think of a computer monitor as essentially ripping off the display off your laptop and sticking it on a pedestal and running a cable up to it. They typically have very few controls. If you go into their user menu or on-screen display menu, they may give you the option for a couple of different color temperatures, like 9300, 6500, 5300, depending on what they offer. They usually only have one color control, and that is traditionally just a saturation control. You usually don't have choice in color gamuts. You don't have choices in gammas. So it's very, very limited. You have the ability to tell it what your white balance is, and what your target color space is, but that's all they deal with. They have very, very, very little color space management, unlike TVs, where we've been pushing the manufacturers for the last 10 years to give us a very rich calibration environment on the TV. On the monitor, they didn't provide that because we can do that in the video output devices or cards within the PCs themselves. So they're relying on the output signal being manipulated versus internally in the display.
Got it. In fact, SoCal Ray Jr. in the chat room, a very good friend of the show and computer whiz, in addition to being a full-fledged calibrator, who you know, Ray Coronado.
I do.
Says you should be able to calibrate the color space and grayscale in the video card, which is exactly what you just said.
Yes, but that's not the only place that needs to be done. And so if we take this as an example, so we buy this display from this monitor, we spend $200 to $300, which is about a medium price now for a 20 to 25 inch monitor for a PC. We set it up, we plug it in, we turn it on. It's going to be fairly blue from the factory. And if we just leave it there, and then we go into our video card and we try to manipulate it there, we're going to create artifacts. We're going to create banding or low light RGB coupling issues because we're trying to move our color space in such a large amount that we're actually creating artifacts digitally by doing that. So if we go back to our video days when we're calibrating TVs, most receivers and AV switchers had some calibration capability. Most output devices, Blu-ray players, DVD players, had some calibration output capability, and the TVs themselves. What we encouraged and taught people to do is fix it in the display first, and then work your way back up the video chain. So we make the display correct by using a reference pattern generator, so we know that the TV is correct to a reference signal. And then we come back one step and we go to the switcher, processor, AV receiver, and we manipulate whatever controls we had in that to make sure its output was to the TV. And then we work our way further back up the video chain to the output device, whether it's set-top box or Blu-ray player, and we make the adjustments in that device to make sure that it is consistent going up to the receiver. So we've got three pieces of the video chain that we need to fix to get the correct signal from your Blu-ray player all the way to your television. If we use that analogy and apply it to our computer technology, we essentially have the same pieces or components. And so we have the display, and we can go in and tell it that we want a 6500 color temperature, that we want this much light output with our backlight control. And so we use those and we set that over the DDC channel. And what that allows us to do is from within CalMan, we can actually control the values that are being managed within the display itself through like kind of a virtual remote interface. So we can, give you sliders and check boxes and knobs to tweak the monitor remotely through software. So we can optimize the monitor before we even try to do anything in the video card. So then we come back one step from that, and then we're looking at the lookup table output of the video card itself. We can manipulate that specifically to do white point and gamma correction in our RGB color space. So we kind of think of that as kind of our intermediate space, like our switcher or our processor or our AV receiver, the device that's kind of changing the signal and switching it and sending it to the output. And then if we go
actually, QNX Monkey, to interrupt for a second, in the chat room mentions that Pro monitors let you set up lookup tables, or what are called LUTs, L-U-Ts, and not on your video card, which he claims is better.
That is true, but the Pro monitors, if you look at like the HP Dream Colors or the Flanders or the Azos or TV Logics of the world, you're starting to get into the $2,000 to $5,000 monitor, which if you're high-end photographer or videographer and you can justify spending $2,000 to $5,000 on a monitor, then you certainly take advantage of whatever the monitor is capable of. But the traditional monitor that you're spending, even we're upwards of $1,000 to $1,200, like the higher-end Dell monitors or the Asus monitors, they still don't have that lookup capability. It's really
in the monitor itself.
In the monitor, only the very, very high-end ones. So that is correct. There are some high-end ones that have it, and if you can afford it, great. But we find that the average consumer that's using these products are typically spending, maybe $500 on a monitor. That'd be a stretch on some of these. If you only paid $500 for your whole computer, you're not going to spend probably much more than that on a monitor.
Right.
But to go back and finish the analogy, so we have our display
please.
that we want to. So the goal is we want to optimize our display by whatever means it's given us. If we only get white balance, we do that. If it's got LUTs, we do that. Then we come back one step and we want to optimize the output of our computer through its lookup table so that it's optimized. And if we go back one step further from that, we want to optimize the output of our application or the operating system, and that's done with an ICC profile. And so we have the same steps in our video chain, the same three steps. We have a source, in this case it's our application. We have a switcher and output. This is the output of the video card to a lookup table. And then we have the display. Just because it's in one box and it's all controlled and you can't have separate knobs, the video path and the steps in the video path are still essentially the same.
Got it. Can you define for us what lookup table means, just so I make sure everybody's on the same page?
So a lookup table essentially is if we send three values in. So we want to say that we want a neutral white color. In the digital world would be a digital value of 128, 128, 128 being red, green, and blue. A lookup table is basically just a three-way index where we take those three values, we go into the lookup table and we say, okay, the input values are 128, 128, 128. What are the output values for that particular index? And they may be 140, 110, 135 to get a corrected output. So basically it's just an index table of input values to output values.
Sort of like a bias for a given display. If you have a certain input, how do you need to bias the red, green, and blue values in order to get the desired image on the screen?
That is correct. I mean, if you look at brightness and contrast, those are bias controls in a display, and they typically manipulate the lookup table in the display, but they're fairly coarse controls. We've only got two, so they affect a very broad area. A lookup table essentially gives us the ability to manipulate the RGB values down to the single 8-bit value. So a lookup table that's in the 8-bit world has 255 input values and 255 output values that map to those input values. So we can essentially move
per color. So there's three times that total.
There's three channels. The red, green, and blue channels is essentially a lookup table. So we can basically remap where the digital values end up.
Got it. Strengths in the chat room is asking, what about different versions of ICC? You mentioned ICC at the beginning, and then you also mentioned it in terms of the application and even the operating system. And Strengths is wondering about different versions. Firefox browser, for example, won't even show colors correctly for web images with embedded ICC version 4 profiles unless you set some parameter here, a very complicated parameter, to true. Only version 2 is supported by default. So what's the deal with ICC version numbers?
ICC version numbers are essentially version numbers like anything. They add additional capability, but they also want backwards capability. And so if we use it kind of in the HDMI terms, we started off with HDMI 1 and now we're on 1.4 and eventually going to HDMI 2. They added a bunch of capability in HDMI 1.4 that version 1 or 1.1 or 1.2 don't have. And so that was essentially the same thing with an ICC version profile. Version 2 had the ability to store the tables in a certain way. Version 4 expanded upon that and gave us a lot more capability. And so the application or the operating system has to be able to use those newer versions. Certainly everything out there should at least be version 2 compatible if they say they support ICC, and more applications, operating systems are adding version 4 capability. Within CalMan, we have the ability to produce ICCs in version 4 or version 2, depending on what you're targeting.
And you mentioned that the ICC profile is what you need to be concerned with when it comes to the application and the operating system.
Yes, and that's where PCs and Macs kind of diverge on the fundamental core of how color works in their systems. Within Mac operating system, the ICC is global and is applied to the operating system rendering color engine itself. And so your applications don't have to be ICC aware or specific. They can be if you want them to be separate from what the operating system is, but they don't have to be. So if you just bring up any application on a Mac and you've loaded an ICC profile for the operating system, the application will inherit it unless it uses something different. On Windows, the operating system is not what we call ICC aware, and so it doesn't provide a factory or global ICC for the operating system. The applications themselves are responsible for being ICC aware and loading the ICC interface into themselves. A good example on Windows is if you bring up Paint or Photo Viewer, those are ICC aware applications that come with Windows. But if you take that same photo and you edit it and you drop it on your desktop as a background, they will look different because the operating system background is not ICC aware.
Okay, so it sounds like with a Windows machine, you need to be a little more conscious of this issue than with a Mac.
Yes, if you're using applications, you need to make sure that the application is ICC aware and it's loading the correct ICC. To go back and kind of define what ICC is.
Yes.
So ICC is essentially a profile. Profiles are not calibration. They're essentially a series of measurements that explain or define how a device is performing. So we go out and we measure all of its reds, all of its blues, greens, its whites, and we just measure them and we store them in a place that we call a profile. Then through fairly complicated math, the application runs that information through an ICC profiler, and they can either shrink, expand, or shift the color gamut or the white balance around based on what the measurement values were. And so that's where the correction happens. The ICC engine output actually does the correction. The ICC measurement and the ICC profile is essentially just a container of measured values.
So does that mean that ideally every computer monitor on the market would be measured and these values stored and used depending upon which monitor you actually have?
That is correct. In fact, a lot of manufacturers provide ICC profiles. You can either download their website, or they come with the operating system, or they just automatically load them in. They're kind of a generic case. As we know in our television land, when we calibrate displays, people are like, well, can I just share my display settings? I've got a Panasonic this model, or GVC, or a Samsung this model. Can I just share? And the answer typically is no, because there's manufacturing tolerances on various components. And so if you're lucky, it may be equivalent. If you're not lucky, it'll get much worse. And so computer monitors, laptops, and Mac monitors are essentially in the same place. They all have tolerances. The manufacturers say, when we source this material and we measured a reference sample, a couple of hundred displays, we said this is kind of what that gamut or that color space looked like for this monitor. So we're going to create an ICC profile based on that. But it's kind of a generic one for that model. It's not specific.
It's averaged over some number of samples that they pulled off the line, but that's a very small sample probably compared to the number that are actually out there. So how accurate is it, or how can you then overcome the tolerances and the variations that must occur from one monitor to another?
That's essentially where our calibration for computers and Macs come in, is we run it through a multi-step process. So if we kind of break it down to what we're going to do in our auto calibration, you hook everything up, you put the colorimeter on the monitor, and we say go. The first thing we're going to do is we're going to measure the total light output of the display and how black it can go. That kind of determines what black and white and how much dynamic range we have to work in. The next step is, if your television or your computer monitor has DDC controls, we're going to go in and start adjusting its white balance and its overall light output to optimize it for the color standard that you chose. Then we go one step further up the video chain. We're going to manipulate the graphics card lookup table output to optimize it for the gamma curve and the white balance that you told us your target was. And now we've done optimization or calibration steps. The final piece of that is we need to create an ICC profile of that exact display's performance as we've modified it. So then we go in and we read a series of red, green, and blue, and then black to white measurements. We store that information, we write it out to the ICC profile, and then load it up for the operating system or the application. So those three pieces together give us a comprehensive profile, what we're calling an ICC plus profile, that we can manage all three pieces together.
Strength says in the chat room, I see people with badly configured monitors creating images that their system embed a bad ICC profile into that corrects only for their monitor. Then they complain when other people's correct monitors show the image badly.
That can be the case. Maybe it loaded the wrong monitor ICC profile, or the monitor got changed. So the ICC doesn't define what mode the monitor's in. It just defines what the monitor is capable of. And so on some monitors, you can go in and tell it that you want an Adobe RGB color space or 709 color space, or a few that you can get into the DCI P3 color space, but the ICC profile doesn't know that. And so if you go in and the ICC profile basically said, hey, I know this monitor is capable of Adobe RGB, that's what my ICC profile encompasses, and then you go into the monitor itself and you set it to 709, and then you load that ICC profile on top of it, you're going to get a much, much reduced color space because they don't match. And so it's just inconsistencies throughout the video chain, and where the colors are mapping, they can give you those kind of problems. And that's what, with our software, that's why we optimize the display first, then the lookup table video card, and then finally create the ICC profile, because then we know they've been optimized and they actually match.
Very good. Well, I know there's more to talk about, and we will get to it in a moment. But for the moment, I would like to take just a second and thank our sponsor for this episode, which is iFixit. Now, iFixit, of course, is an amazing resource. It's a website, ifixit.com, that is probably best known for its teardown of devices. They actually go in and take apart things and see how they work and how we can fix them. And that's really the most important part of what they do. It's an online community they offer over 10,000 repair guides for everything from your smartphone, computer, tablet, game console, to home appliances, even your bike. It's like having a free online repair manual for everything. And this is really the key to the power of iFixit. If you've shattered your smartphone screen, you want to repair your game console, or you need to swap out a battery on your tablet, not always an easy thing to do, iFixit has you covered. They can even hook you up with parts that you'll need to do it, and everything they sell is tested and guaranteed. iFixit also makes the most trusted repair tools for consumer electronics, including the ProTech Toolkit. Now, I have to tell you, they sent me one of these ProTech repair toolkits, and it's a marvelous thing. It's in a great soft case with 70-something tools in it, including a 50-piece driver set with everything like Torx and very odd kind of driver systems that Mac, Apple, and various other people wouldn't want you to be using to open your product, but it's here. It's right here and ready to use. My favorite tool is the spudger, which lets you remove certain items from the motherboard and so on that you wouldn't otherwise be able to remove. It's just a super cool toolkit that I've had plenty of occasion to use already when replacing memory and doing some other things on the computer, my laptop, that would otherwise be very difficult. So it's really quite remarkable. This toolkit is what you really need to get started. Then you access the repair manuals online, and that gives you the information you need to use the tools you now have to fix anything that you have in your electronic arsenal. 54-bit driver kit I mentioned, with Torx and Torx security bits, tri-wing bits and triangle bits. Yes, the nylon spudger for prying and scraping things. Now, this toolkit is only $64.95 and is backed by a 1-year warranty. Hobbyists and home DIY fixers can also use this ProTech toolkit for doorknobs, eyeglasses. It's another thing I've actually used it for already. Cabinet doors, sink fixtures, and more. If you're looking for a great addition to the artist's or hobbyist tool chest, look no further. Best of all, as I said, there are thousands of free iFixit guides to help you use the tools to get the most out of your products. Repair is noble. E-waste is a huge problem. Why pay someone an arm and a leg to fix it when you can do it yourself? Be part of the solution and repair your own electronics. With iFixit, you can fix it yourself. Visit ifixit.com/twit for free step-by-step guides. iFixit also sells every part and tool you'll need. Plus, if you enter the code HTG at checkout, you'll save $10 on any purchase of $50 or more. So right there, your Pro Toolkit is $10 off. So be sure to visit ifixit.com/twit. And we thank iFixit very much for their support of Home Theater Geeks and the entire Twit network. Okay, so we've been talking all about making sure that your computer monitor is calibrated in such a way as to show you what your photos and your videos are going to look like when you play them on something else like a TV or a consumer projector, or if you print them out. And that's kind of a different story. Does SpectraCal CalMan deal at all with hard copy printout? Because that's kind of a different process than video display.
No, we don't. We don't get into the print side of it. That's a fairly competitive industry. The people that are in it now do a very good job. And the measurement devices are, in fact, different.
Well, for one thing, as I understand it, the displays like computer displays, TVs, and so on are emissive and are therefore what we call additive, which means you add red, green, and blue together to get white and all the different colors. Whereas in the print medium, it's subtractive, and you actually have to take away colors to change the actual color that you're getting.
Yes, and that's why the measurement devices and the processes are different. So for example, if you print out a piece of paper and you want to effectively measure what was printed on that, you have to have one way of illuminating the colors on the paper itself and then also measuring them back. And so that's typically when we get into the spectrophotometers, like we have from X-Rite and other manufacturers. And those are typically much, much more expensive than the emissive type colorimeters that we use for display calibration. So it's kind of a different industry, different marketplace. Still color science, and yes, one is additive and one is subtractive. But ICC profiles or calibration essentially is trying to achieve the same thing. So you have a consistent or an industry standard output or input for those devices.
And you mentioned LUTs or lookup tables before, and am I correct that what the example you gave, that you have a value of 0 to 255 for red, green, and blue, is what would be called a one-dimensional lookup table or LUT?
Yes. So typically in a video path of most output devices, or the video path on an input device on a television display, they typically all have input LUTs and output LUTs, whether we can get to them or not. They're usually designed into their chipsets. And they're typically a one-dimensional or 1D LUT, in that red has its own lookup table, green has its own, and blue has its own, and they don't interact or affect each other. There are also two-dimensional lookup tables, and there are also three-dimensional lookup tables, so full volume color spaces when we get into three-dimensional lookup tables.
Can you explain a little bit more about what three-dimensional lookup tables would be? I mean, I assume that they're like cubic patterns.
No, in fact, they are cubic. And instead of saying 3D lookup tables, because then people often confuse them with 3D stereoscopic, because 3D was kind of overused for the industry for television displays. We often refer to them as cubes or cubes, color cubes, cube LUTs, instead of calling them 3D, even though technically they are. So yes, cube is a more descriptive word for what they actually are. And if you look at a cube, it has, essentially 6 sides and 6 points, and it has a volume of area on its inside.
Actually, it has 8 points.
Or sorry, 8 points, yes. 6 sides, 8 points. And it has a volume of area on its inside, and then non-volume of area on the outside you can't get to. And so 3D cubes or lookup tables are essentially just describing what that volume of space looks like. And so then we take 3 input values, but then we have to then index anywhere into the X, Y, and Z coordinates within a color space or within a cube to then determine what the output of those are. So we're actually using a 3-dimensional index instead of a 1-dimensional index.
And does that give you better accuracy, greater range? What's the advantage?
That gives us the ability to manipulate any input value to any output value for the entire color space. So we can change what the very darkest blacks, blues, greens, or any color at the bottom are. We can change what the very whitest colors are that are near full saturation, all the way to the edges. And so if we think of our 1D lookup tables, and we take our cube and we stick it so black is on the bottom and white is on the very top, kind of like a pyramid shape. So we've got points at both ends. Our 1D lookup tables essentially intersect right down the center of that. And that's the only thing it affects, is the very, very center of this cube. And so we have very limited control. We can adjust what our whites look like and what our blacks to whites look like through the center of that cube, but we don't have control over the entire volume like we do with 3D lookup tables. And so 3D lookup tables just expand that concept of doing manipulation of our white balance to the entire color space or the entire color volume.
This is exactly what I was about to mention. At the SMPTE Tech conference that you and I were both at a week before last, they talked about the importance of considering color volume. Normally, we take a look, we see a diagram called the CIE color diagram, and I'm sorry I don't have one handy to put up and show everybody. It looks kind of like a horseshoe. It's very multicolored. It's got a green area and a red area and a blue area and stuff in between. But that only represents the colors at a particular brightness. And what really we need to do in order to fully evaluate the capabilities of any display, computer monitor or TV or projector or whatever, is to take that diagram into the third dimension and create a color volume which describes how many colors can be represented at different brightness levels. So is this what you're talking about here?
Yes, that's exactly what we're talking about, is essentially the color volume and the ability to manipulate any point from within that color volume, just not the white spline that's down the center like we've typically done with 1D LUTs.
Okay. And CalMan uses 3D LUTs, I believe, correct?
Yes, we just recently added, we're on our third generation of 3D LUT technology. When we started going into the Hollywood or studio spaces, their monitors, their processing engines, their output software all deal with 3D LUTs. Traditionally, those 3D LUTs were used for what they call creative. And so if a producer or a colorist or the director said, you know, I want my movie to have kind of a green cast over everything, then they would shift the whole color space towards green. And that's the color space that they would work in. Or if you wanted certain colors to have a muted tone, but as you approached your fully saturated colors, they become more vibrant. And so they do those for a creative effect. They can manipulate this color volume or space, and they can move various points around, stretch them, squish them, twist them within that space as a creative element in what they were producing as part of their story.
I'm thinking in particular about The Matrix.
Exactly. That's why I mentioned green. That's a very good example of a kind of a green cast or hue on the entire movie. That was an intent.
Right. It wasn't actually the entire movie. It's only, I think it was only when they were in The Matrix that there certainly was a distinctive green cast to everything.
Yeah. Another good example is all of the CSI shows. So if you look at CSI Las Vegas versus New York, and when Miami was on, they all had different color palettes. They all had different looks. CSI in Miami had a very saturated, very vibrant look. CSI New York has a more muted saturation tones, and CSI Las Vegas is kind of somewhere in between. And so they choose those as a creative effect to give you an emotional connection of that space. If you're in Miami, it's supposed to be very vibrant, very bright. You got a lot of sea, a lot of sky, and so they overemphasize those areas. In New York, it's supposed to be, you know, less of that, a bit more dingy, more edgy, and so they change the color palette of the space they're working in. And so that's their creative space that they can work in. And so they've been using 3D volumetric or cube spaces to basically help tell their story. Recently, we've been able to then also produce 3D LUTs for corrective. So we can go into a display and we can measure and we can say, okay, the display, we fixed its white balance, we fixed its gamma, we fixed its outer edge saturation points. But what happens when we're looking at, you know, a 22% blue with this much brightness in it? You know, what happened in that area? So we can basically measure hundreds or thousands of points within the volume or the cube space and then correct those so that the display is truly RGB additive. So we talked about RGB additive, important for emissive devices. That's how they work. You've got to be able to add red, green, and blue together in a linear fashion and produce any color from that. And if your display has non-linear issues in that when you add red, green, and blue together, you don't get what your intended output was, then you have deficiencies in your display. You can correct those with a 3D cube or a volume.
Now, can your software, which is running, I guess, on the PC that you're calibrating, let me start there. Is that generally the scenario you would be talking about? You would be running CalMan on the computer that you're trying to calibrate the display of, or would you be running it on a separate computer doing the measurements like we do with TVs?
There's a number of scenarios. For the independent that's just starting out, they're probably running their software either on a Mac or PC. Their output of their device is connected to a computer monitor, maybe even a TV, a plasma, but it's the computer output that's controlling it. And so we can traditionally just use the CalMan RGB, which we just released for that. If you're using an output video device, which is different from your output video card, And there's a number of companies that produce those. So Blackmagic Design, AJA produce these cards that you can put in your computers if you have a tower, or Thunderbolt devices that you can plug in via your Thunderbolt output that essentially become video output devices. The operating system has no control over it. It's just the software uses this as a video output conduit. When you're running those software interfaces, they have the ability to load up 3D lookup tables within their software to then control that video output space separately from the normal operating system output.
Mm-hmm. Sorry, you about to say something?
Yes. So that kind of describes the two scenarios, how you would use this. So if you're using, like DaVinci Resolve or some of the Adobe products, it kind of depends on what your video output is. If it's just the native output of your laptop or PC, then you can do that with DDC lookup tables and ICC profiles. If you're using a dedicated video output device, and you want more control and more correction, then we can actually load corrective 3D lookup tables into those pieces of software or even hardware.
Mm-hmm. But then that information, those lookup tables, need to be there whenever you're working, so that the proper correction is applied to the monitor, right?
Yes. And so if we kind of go back and look at our knowledge of where things are being corrected, there's a number of display manufacturers that allow us to load 3D lookup tables directly in the display themselves, and there are more coming out. For the ones that don't provide that, then you can have an external box from like Davio. They had theirs. Pluto has theirs. Fujifilm has theirs. There's a number of boxes that will store 3D LUT and manipulate the signal as it goes through. And there's a number of software packages that you're running on your computer itself that you can load the 3D LUT into its output. So it kind of just depends on what kind of equipment you have and where you want to load that corrective 3D LUT versus the creative 3D LUT.
Mm-hmm. Mm-hmm. T. Joe Code for Sale LLC, quite a mouthful for a chat room name, is asking a sensitive question, but I'll ask you. What about competitors to your system? What do they do anything differently? I won't ask you to ask whether they're better or not, because that's an unfair question. But what do your competitors do differently from you anyway?
We have competitors in all the spaces that we're in. And the reason our products exist is because we felt there were better ways of either accomplishing a better result or easier to use. And that's essentially what we do as a company. We find niches where they're not being addressed or under-addressed or not being well addressed, and we go after those. So in the ICC market, the traditional manufacturers, the Data Colors, the X-Rights of the world, that actually manufacture the color measurement devices. They have their own software. Their software is geared more around, or traditionally has been more geared around single purpose, single use. I want to calibrate my computer for editing photos. I want to calibrate my computer for doing some task. And with CalMan, we understand that people are using their computers for a number of things today. I'm a videographer, I'm a photographer, I'm watching videos I'm watching Netflix, or I'm playing Blu-rays back on my computer. We're using them for a lot of different things. And so we chose that we need to have the ability to easily switch between what we call profiles. And so we have a tray application running, whether it's a PC or Mac. You just right-click on it, and if you've created profiles for DCI and Adobe and 709 or what other color spaces, you can easily toggle between those as you're using your computer for different purposes. So that's kind of where we broke away and said, hey, we know people are using their computers for a lot of different things versus single purpose. Mm-hmm. So that's why we can. Sorry, go ahead.
I was going to say that's how you distinguish yourself there.
Yes.
Burke in the chat room is mentioning you can do this over a network.
Yes, and that was also another capability that we wanted to add is you install our client software on the computer, basically the target output device, and then CalMan itself can be on a computer anywhere else, remotely or in the room, talking to it over a network. And so a good example is we have a couple of large customers in Hollywood that do graphics editing and for their movies and various other things. And they may have, 20 different editing workstations. They don't want to have to install CalMon on every single one of them. So they install our Client 3 on all of them. And then a technician goes around with his laptop running CalMan and connects to each of those stations over an IP address and just puts the monitor on the probe, press the calibrate button. 2.5 minutes later, he goes to the next one, presses the calibrate button. 2.5 minutes later, does the next one. And so we leave a resident piece running, but we talk to that over an IP address. So there's no physical connection between the computers, and you don't have to install CalMon on every single computer. Mm-hmm. Unlike our competitors, we have to install their entire package. All their device drivers, all the control stuff have to be installed on every single computer. And then you physically have to plug the probe into each of those computers as you're calibrating them. In our environment, you just install the essential pieces on the target platform and then let CalMan control it all remotely.
Mm-hmm. You mentioned also the probe, or the actual physical measuring device from X-Rite. A couple other companies make them, I'm sure. Do any of them work better than others? Are there some things that people should be aware of when considering which measurement hardware to acquire?
We support every device that's out there. So it's kind of a tricky question to answer.
But for example, there are some probes that are what are called tri-stimulus, which means they are already set to they have filters in them for a certain color of red, green, and blue. Whereas there are then something called a colorimeter or a spectroradiometer, which can detect all kinds of different colors of red, green, and blue. So I'm asking you really about the difference between those. The tri-stimulus meters are typically less expensive, but then you have to have a lookup table for them, don't you, in case you have a monitor that has a different color of red, green, and blue?
That is correct. Colorimeters or tri-stimulus devices need a lookup matrix to basically describe what the target display is doing versus what their filters were designed for and the differences between those. For a spectroradiometer, typically costs 2 to 5 times more in the same class, but that has the ability to read the light in multiple spectrums. They both have advantages and disadvantages. The disadvantage of a spectroradiometer is, since it's reading the light, breaking it up into very small pieces, the sensitivity at low light is very inefficient, to where on tri-stimulus devices it's very good. And so it kind of depends on what you're using it for and what your target is. We have our measurement devices that we have built for us by X-Rite, our C3 and C6. They're optimized for specific display technology. So our C3 is optimized for LCD, whether it has a CCFL backlight or an LED backlight. We've also added plasma capability to it. And then we have our C6.
Not that that'll be useful that much longer, I suppose. Huh?
Yeah, Pioneer's getting out of or Panasonic. Yeah, it's getting out of that.
Panasonic's getting out of the plasma business.
Unfortunately. We're having talks with them next week, so we're going to try and twist their arm, at least do something. I don't know.
Oh, good. Please do. Please do.
I'm sure it's high level. They want those factories for other stuff, building other newer types of display technologies, solar panels, where the money is. And obviously plasmas aren't where the money is anymore.
No, afraid not.
But we do have our C3 and C6. C3 is designed for a handful of devices. The C6 is designed for a lot of devices. In fact, it could be field upgraded. So as newer display technologies come out, we measure them in the lab. We find out what their spectral response is. We create a global offset. We actually put that in our software so that next time you connect the colorimeter, we download it to the device. So you don't have to send it back to us as backlight technologies change.
So have you looked at quantum dot backlights? Have you developed?
They're phenomenal. In fact, if we could just skip over the whole OLED thing and just go right to quantum dot, I would absolutely love it. We were working with, and the reason I'm saying that is we were working with Nanosys Display Technologies. They were in our booth. This is 4 years ago. We had them on an end cap, and we didn't have much literature around it because they just built it, and this thing came out of the box, and it still didn't have like the really nice edge bezels. And people were walking by and they're like, "Is that the new plasma?" I'm like, "No," because it was very bright. It produced a lot of color and had a really wide viewing angle. Or no, that's an LCD. And they're like, no, that can't be LCD. That's got to be an OLED or a plasma. It's like, no, this is quantum dot. And so we got a very, very early look at what quantum dot was capable of. And at the time, I predicted it would probably be 3 to 5 years before we started seeing a large number of quantum dot displays coming out. That still really hasn't happened a lot. There's only a handful of manufacturers that have come out with quantum dot because they've got so much invested in OLEDs that they have to go down that path first to recoup all their engineering and kind of push the market that direction.
Oh, yeah, but the yields on OLED are so low that it's going to remain very expensive.
Agreed. One of the devices I was just reading about, I got an email from one of my engineers and said, go look at the specs, the actual specs on the Kindle Fire. Is it the HDX that they just came out with their new one? That's actually that's actually using a quantum dot display.
Really? Well, let me
just advertising it. Yeah.
But they're not advertising it. Let me quickly just explain to people really quick that what quantum dot technology is it's a new form of backlight for LCD TVs and other kinds of LCD displays. Instead of an LED behind the LCD panel, instead of a fluorescent light behind the panel, there is a film of these tiny, tiny, tiny little dots. It's a form of nanotechnology, really. And depending on the size of these little dots, when they get bombarded with blue light, and we get back to blue LEDs here finally, blue LEDs are often used to bombard these little tiny dots with blue light. And depending on the size of the dot, they'll either glow red or green. And that combines to form white. So it's a very promising technology. Sony uses it in what they call their triluminous displays. I don't know who else has one now. Derek, do you?
No, there's very, very few manufacturers. In fact, Sony was one of the partners in the technology. I know most of the display manufacturers were partners, and Sony was going to be one of the first ones to release the technology. But Sony has a lot invested in their OLEDs. And so, yeah, I think I just was kind of hoping we were going to skip over OLEDs and go right to quantum dot.
Well, OLED has its advantages too. I mean, the viewing angle is probably even wider. LCD panels still suffer from some form of viewing angle problem. I can't imagine how quantum dots could really solve that problem. It's just a backlight technology.
They actually got rid of the diffuser. In a quantum dot LCD LED-based display, you don't need a diffuser. You don't need to
that improves the viewing angle
or polarize the light as it's going through the color filters. And so that improves the viewing angle. What it doesn't fix is the ability to turn light on or off. LCDs are very inefficient at that. You can't totally turn an LCD off, so they have light leakage.
Right.
Unlike OLEDs, when they go off, they are off. There is no light coming out of them. They essentially have infinite black.
Which is why they have such a great black level, right?
So my ideal display would use an OLED white or blue backlight through a quantum dot diffuser panel on the output. And I'm sure there'll be hybrids coming out with something like that someday.
Maybe we'll see him at CES this year.
It's entirely possible.
Right. Well, listen, I want to thank you so much for being here. It's been very instructive for me personally, because I didn't know that much about computer monitors or anything like that. But I have been concerned, as I said at the top, about how my photographs look on my computer monitor versus how they look on a TV. And now I know I can get them to be much closer thanks to SpectraCal and the new version of CalMan. So thanks for that, and thanks for all your great information here today.
All right, thank you, Scott. We enjoyed being on the show. And if anybody has any information, it's on our website, or contact me personally or through Scott. Yeah, we're real excited about being able to offer PC calibrations to the same level of quality that we've been able to in the television and studio markets.
Yep, absolutely. And that website, of course, is spectracal.com, spectracal.com. You can find me, of course, at avsforum.com. You can email me at scott@twit.tv. And you can follow me on Twitter at htgeekscott and also at avsforum. And you can also find previous episodes of Home Theater Geeks right here on twit.tv/HTG and on our YouTube channel at youtube.com/twit Home Theater Geeks. Next week's guest geek is still not finalized. So there are a few candidates that I have on the line as possibilities, but you'll just have to tune in then to find out who I managed to snag for next week's show. It'll undoubtedly be somebody very interesting with lots of great stuff to talk about in the realm of audio and video. So I do hope you will join me and be surprised. Until then, geek out.